Good morning, class. Today we're going to talk about complex numbers in trigonometric form. Trigonometric form is also known as polar form. So if you see polar, that is what it means as well. All right, today we're going to plot complex numbers in the complex plane. We're also going to plot them in the polar plane as well. We'll find the absolute values of complex numbers, which is also called finding the modular portion of a trigonometric form or polar form. We'll write trigonometric forms of complex numbers. We'll multiply and divide them. We'll also find powers of them. We probably won't get to nth roots. Okay, so just as a real number can be represented by points on the real number line, you can represent a complex number, z, which we will say is equal to a plus bi, as the point a comma b in a coordinate plane. All right, so the complex plane will look just like your typical coordinate plane with your x and y axis, except instead of an x and y axis, the horizontal axis, which is usually our x-axis, we will call the real axis, that's where we will plot the a, and the vertical axis, instead of being called the y-axis, will be called the imaginary axis, and that will be referenced by b. All right, the absolute value of a complex number, a plus bi, is defined as the distance between the origin and the point a comma b. Right? The absolute value of the complex number is z is equal to a plus bi, is given by, we could just put that in our typical absolute value signs there, and that is equal to the square root of a squared plus b squared. Right now, many of you on the last, well, not the last test, but on one of the last trig tests that we took, all right, still are making the very bad mistake of when you have the square root of the sum of two things squared, all right, you just take the square root of each piece. All right, that is not allowed with addition, right, or subtraction. It is only allowed with multiplication or division. So do not make the mistake of thinking that this is the same as a plus b. It is not. Right, a lot of you are still making that mistake. All right, when the complex number a plus bi is a real number, that means that the imaginary part, b, is equal to 0. This definition agrees with that given for the absolute value of a real number. Right? So, of course, plugging it into our equation, we would just get the absolute value of a. All right, so let's plot in the complex plane, right, the complex number -2 plus 5i. All right, so first we will get some axes on here. All right, and then all right, so this is my real axis. Oops. And this is the imaginary axis. All right, so remember this corresponds to a comma b, which is -2 comma 5. So we would plot it just like we would plot any point, like we used to back in pre-algebra. So -2, 5 would be right here. That's it. It is that easy. All right, we can do the same thing here. All right, so again, this of course would correspond to the point 6, negative 2. So we go 1, 2, 3, 4, 5, 6, negative 2. So right in there. All right, so of course, a plus bi is the standard form of a complex number, which is also often referred to as the rectangular form. All right, so standard and rectangular form is a plus bi. Trigonometric form, which can also be called polar form, all right, of a complex number, all right, can be represented as z is equal to r times cosine theta plus I times sine theta, all right, where A is equal to R cosine theta and B is equal to R sine theta. All right, so R is actually the same as the absolute value, all right, of A plus BI, which is the square root of A squared plus B squared, all right, and we find theta, our angle theta here, right, by using the fact that tangent of theta is equal to b over a. All right, the number r is called the modulus of z, and theta is called the argument of z. Right, and those terms will, you'll see those on delta math, your delta math assignments. So to make sure that we understand what those are. All right, so your modulus here is r, all right, and your argument here is theta. All right, so do keep that in mind. All right, the trigonometric form of a complex number is also called the polar form, like I said, because there are infinitely many choices for theta. Remember, there's infinitely many coterminal angles of any angle in standard form. All right, the trigonometric form is usually restricted to 0 to 2 pi. Right? Although on occasion it is convenient to use a theta less than pi. All right, so sometimes they like it 0 to pi, but usually 0 to 2 pi. Okay, now this is what's called the polar plane. All right, and we can also graph these. This is the modulus and this is the argument. All right. Now this is in degrees. All right. Typically, you'll also see them often in radians. All right. So either way, it works the same way. All right. So this really corresponds to 2 times cosine of negative 255 degrees plus I times sine of negative 255 degrees. All right, so this is my R and this is my theta. All right, now we don't, typically we like between 0 and 2 pi, or in degrees 0 to 360. So we don't like this negative 255. That's okay. To find a coterminal angle, all we have to do is add 360, and that takes us to 105 degrees. All right. So what we want to do is go to 105 degrees. All right. So that would be right here. Right. 105 is exactly halfway between 90 and 120. All right. Of course, there's 30 degrees difference between here, so halfway between that would be 15, so this would be 105. All right, and then we go 2. That basically tells us how far out from the center we go, right? So of course the origin is 0, 1. So this whole ring is 1, right? 2, this whole ring is 2. 3, this whole ring is 3, etc. All right. So because this 2 right here, we know that we have to be on the 2 ring, right? And then we know that our angle, negative 255, which is the same as 105. So I go here to 105, I plot it on that 2 ring, and I'm done. So very easy once you kind of understand the premise. Right, here we can do this again. Right, now we are back in radians here. All right. So with the negative number, it's a little bit different, but not really. All right, let's go ahead and find our angle first. So this is 23 pi over 12. So let's go ahead and change some of our obviously this is almost 2 pi, so it should be down here somewhere. Let's change this to a common denominator, which would be 1 with 12. All right, so this would be 22 pi over 12. All right, 2 pi, which is the same as 0, would be equal to 24 pi over 12. All right, so 23 pi over 12 should be right between these two. So this right here is 23 pi over 12. All right, so we're going to be on this line. All right. Now, it says to go negative 3, right? Well, of course, this would be positive 1, positive 2, positive 3, positive 4. So we kind of want to stay on this same line here, but go in the opposite direction. So this would be negative 1, negative 2, negative 3. We would actually be right here. All right. Which is also the same as making this positive and subtracting pi from this. So either way that you want to think about it. Okay, so let's write the complex number z is equal to negative 2i in trigonometric form. All right, so we know that in order to write it in trigonometric form, all right, we are going to need r and we are going to need theta. All right, now this is the same thing as z is equal to 0 minus 2i because there's no real part to this complex number. Okay, so my a is 0 and my b is equal to negative 2. And that, of course, comes from z equal to a plus bi, the standard form or rectangular form of a complex number. All right, we know that r is equal to the square root of a squared plus b squared. So in this case, that is the square root of 0 squared plus negative 2 squared. So 0 squared is 0, negative 2 squared is 4, 0 plus 4 is 4, so r is equal to 2. All right, now to get our theta, we use the fact that tangent of theta is equal to b over a. All right, well, in this case, tangent of theta is equal to negative 2 over 0, which we know is undefined. Okay, well, we think that doesn't help us, but it actually can. If we think about our unit circle, all right, where is my tangent undefined? All right, well, my tangent is going to be undefined here at pi over 2, and at 3 pi over 2. Okay, so this is where my tangents are going to be undefined. But again, that's just from the unit circle. All right, so now we need to determine, okay, well, which one of these is it going to be? Well, let's think about where this would be if we graphed it, all right? Just like when we were graphing these points up here, okay? So in standard form, where would this thing be if we're graphing it? Okay, well, if I'm going to graph 0, -2, so 0 keeps me on the y-axis, -2 would be down here somewhere, so that's going to be 3 pi over 2. All right, so now I know that my theta is equal to 3 pi over 2. So now I can go ahead and write my z, right, in trigonometric form, right, and that is going to be my r, which is 2, times cosine of theta, which is 3 pi over 2, plus I times the sine of theta, which again is 3 pi over 2. And we're done. All right, that's it. That is my answer. Okay, let's try this again. All right, again, when watching this video, I would highly recommend pausing it, trying to work it out on your own, and then watching to see if you did it correctly. All right, so we're doing the same things here. Right, this is essentially, since there's no real part, this is 0 plus 3i, which means a is equal to 0 and b is equal to 3. All right, so my r is going to be equal to the square root of 0 squared plus 3 squared. That's a 0 plus 9. The square root of 9 is just 3. So r is equal to 3. All right, again, we know that tangent of theta is equal to b over a. So this is going to be 3 over 0, which again is undefined. All right, but if we were going to graph this on our rectangular plane, we would graph 0, 3, which would be up here somewhere. Again, remember this is pi over 2. This is 3 pi over 2, the two places at which tangent is undefined on the unit circle. So we know that from this, theta is equal to pi over 2. Well, now I have my r, I have my theta. We know that the trigonometric form is r is equal to, z is equal to r times cosine theta plus I sine theta. All right, so you can write that. Z is equal to my r is 3, and my theta is pi over 2. Done. Okay, so now we'll get to ones where our tangent will not be undefined. All right, so here my a is -2, our b is -2 square roots of 3. All right, so again, I'll find my r first, which is the square root of a squared plus b squared. All right, so that will be -2 squared is 4 plus -2 squared is 4. The square root of 3 squared is 3. 4 times 3 is 12. 4 plus 12 is 16. The square root of 16 is 4. All right, now we just need to find our theta. So we know that tangent of theta is equal to b over a. Well, my -2's will cancel here. So this is just the square root of 3. All right, Again, if we look at the unit circle, of course this is one of our nice values on the unit circle. On delta math, oftentimes they will not be. That's fine. All right. All you have to do is take the inverse tangent, right? Of course, remember, the inverse tangent is only going to give you a value between negative pi over 2 and pi over 2 if you're in radians, or negative 90 degrees and 90 degrees if you're in degree mode. All right. So you will have to use the fact that the period of tangent is pi, or 180 degrees. So you'll have to add that accordingly enough times to get to the proper angle, all right, which, could definitely be in quadrants 2 or 3, which the inverse tan function on your calculator will only give you an angle in quadrant 1 or 4. So do be mindful of that. And you figure that out just by plotting it, what quadrant would I be in, and then you add pi enough times to get there. All right, but in this case, this is on the unit circle, all right? Tangent is equal to the square root of 3 in a couple of places, all right? That occurs at pi over 3, right? And it also occurs at 4 pi over 3. So we need to say, okay, which one of these is it? All right, well, if we were to graph, all right, and that's not very well done there, all right, it would be somewhere like that. But, yeah, whatever, I'm not doing very good with that, so we won't really worry about it, but just imagine where pi over 3 would be, which is up here somewhere at 60 degrees, and 4 pi over 3 is down here, all right, at 240 degrees. So we need to figure out which one of these we're going to use. Well, if we're going to graph this point, this would be negative 2 comma negative 2 square roots of 3. So negative 2 over here, negative 2 square roots of 3 would be down here somewhere. All right, so my theta has to be 4 pi over 3 because I'm in the third quadrant here, right? If when I graphed this I were in the first quadrant, then I would know that it was pi over 3. Okay, well now I have my r and I have my theta, so I can easily write that. Z is equal to 4 times the quantity of cosine 4 pi over 3 plus I times the sine of 4 pi over 3. And we're done. All right, again, you may want to pause this, attempt this on your own, and then play to check yourself. All right, again here, my A is 6, and B is negative 6. So if I do R is equal to the square root of A squared plus B squared. All right, this is 36 plus 36. So this is the square root of 72, all right, which obviously is 36 times 2. So this is 6 times the square root of 2. All right, tangent of theta is equal to B over A. So that's just negative 1. All right, well, tangent is equal to negative 1 at a couple of places on the unit circle, namely 3 pi over 4 and 7 pi over 4. All right, so this would be in the second quadrant, and this would be in the fourth quadrant. Okay, so if I went to actually graph this, 6, negative 6, 6, negative 6 would be down here. So that would be in the fourth quadrant. All right, so I know that my theta has to be 7 pi over 4. So Z is equal to R, which is 6 square roots of 2, times cosine of theta, which is 7 pi over 4, plus I sine of theta, which again is 7 pi over 4. And we're done. All right, so write the complex number in standard form, a plus bi. So now we're going the other way, right? We're starting in trigonometric or polar form, and we're converting to standard or rectangular form. All right. This is actually a little bit easier. All you have to do is simplify, right? Using usually unit circle values, right? But if not, right, if it's something that's not on the unit circle, then you just plug it into your calculator and use a decimal representation. All right. Well, negative pi over 3 rather, is the same thing as if we only like positive values, since that's what we have on our unit circle, we can add 2 pi here, which is 6 pi over 3, right? And that would give us 5 pi over 3. All right, so now we look at our unit circle, all right, and we say, okay, well, what is the cosine of 5 pi over 3? All right, and that happens to be 1/2. All right, and what is the sine of 5 pi over 3? That happens to be negative square root of 3 over 2. Well, now we just go ahead and distribute this square root of 8. All right, do be mindful that the square root of 8 is equal to the square root of 4 times the square root of 2, which is equal to 2 square roots of 2. All right, so I'm going to think of this as 2 square roots of 2. So now when I distribute, I'm going to get 2 square roots of 2 over 2, which that would cancel here, all right, plus I times, all right, 2 square roots of 2 times square root of 3, of course we're going to have a negative out here, that would be 2 square roots of 6 over 2, so these would cancel, all right, so putting that in a plus bi form, this would just be the square root of 2 minus the square root of 6, I. All right, now you can put the I in front of the square root here, and sometimes you will often see it like that, just so that people don't confuse the I being underneath the square root. All right, I like to put it at the end because it looks more like a plus bi, the standard form. But if you do that, make sure that it's very obvious that the I is outside of the square root. All right, we can look at another example. So again, you may want to pause it here, try it on your own, and then push play to check your answer. All right, so here we've got 8. All right, the cosine of 2 pi over 3 is negative 1/2. All right, and the sine of 2 pi over 3 is the square root of 3 over 2. Now we just distribute this in 8, so we will get negative 4 plus 8 over 2 is going to be 4, so 4 square roots of 3, I. And that's it. All right, product and quotient of 2 complex numbers. All right, so if we have 2 complex numbers, z1 and z2, to multiply them, all we do is multiply the r's and add the thetas. All right, to divide them, we do the opposite. We divide the r's and we subtract the thetas. All right, so very straightforward. So let's find the product of these 2 complex numbers. All right, So z1 times z2 is equal to, well, I take r1 times r2, so 3 times 2. I guess I'll bracket. All right, and then I will have cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Okay, now, when it wants us, when it gives it to us in complex form or in trigonometric form, answer in trigonometric form. Okay, so you don't have to, by any stretch of the imagination, simplify that and put it in standard form. All right, so of course 3 times 2 is simply 6. All right, and pi over 4 plus 3 pi over 4 is simply pi. And that's it. All right, we're done. All right, now, of course, if it asked you to put it in standard form, it would be relatively easy, all right, to just simplify this using unit circle values and distributing and whatnot. But typically, when it gives it to you in trigonometric form, answer in trigonometric form. And if it gives it to you in standard form, answer in standard form, unless it asks you to do it in the other. All right, so here's another example. So again, this would probably be a good time to pause, try it on your own, and then push play to check yourself. All right, so z1 times z2. 7 times 3 is 21. All right. Cosine. 3 pi over 2 plus pi over 2 is 4 pi over 2, which is 2 pi. All right, now a lot of times, like was mentioned earlier, when you give a number in trigonometric form, oftentimes they want theta to be between 0 and 2 pi, not counting 2 pi. All right, so especially on delta math, if they do this and like you type this answer in and it tells you you're wrong, that would probably be just because they want you to, whoops, sorry, not theta, actually 0. Because they want you to write the coterminal angle that is within this range, which in this case would just be 0. Done. All right, so here we're going to do the same thing, except now they don't have common denominators, so you would have to get them, right? That's fine. This would just be 4 pi over 6. So z1 times z2. 2 times 8 is 16. And then we add our thetas, so that would be 15 pi over 6 plus I sine of 15 pi over 6. All right, so same concept, very straightforward. This is between 0 and 2 pi, so we're good. All right, same concept here. This is going to be 2 pi over 6, just to get a common denominator with these down here. So z1 times z2, 3 times 4 is 12. Cosine, 2 pi over 6 plus pi over 6 is 3 pi over 6, which reduces to pi over 2. Again, do make sure you reduce those, especially when you're working on delta math. Okay, so now we're going to do the quotient. We're going to be doing division. So remember, now we just divide the r's and we subtract the thetas. So z1 over z2 is going to be equal to 24 over 1, all right, times cosine of 300 minus 75 plus I times sine of 300 minus 75. So of course that will just equal 24 times the cosine of 225 plus I times the sine of 225. And we're done. So again, very straightforward, right? Again, like usual, you may want to pause it here, try it on your own, and then push play to check. Z1 divided by Z2. 1 divided by 1 is 1. Times cosine, 40 minus 10 is 30. Plus I times the sine, again, of 30. Very straightforward, straight from the formula. All right, so now powers of a complex number. This is called De Moivre's theorem. All right, so if we have, again, an imaginary or complex number in trigonometric form, all right, and n is a positive integer, then we can raise, this complex number in trigonometric form to a power simply by raising the r to that same power and multiplying the theta by that power. All right, so again, with this formula, it's very straightforward. We're just kind of plugging things in. All right. Now here, right, obviously, this would be a crazy pain in the butt, all right, to try to do this when it's in standard form, right? You would literally have to multiply this thing out 12 times, or if you remember Pascal's triangle, you could use that for binomial expansion, but even that is going to be kind of annoying, all right? So what I'm going to do here, this is my A, this is my B, is first I'm going to change it into, change this to trigonometric form. So my R is equal to the square root of A squared plus B squared. All right, so that's 1 plus 3, which is 4. The square root of 4 is 2. All right, so tangent theta is going to equal B over A. All right, and on the unit circle, the tangent is square root of 3 at pi over 3 and 4 pi over 3. All right, of course, if we were to graph this thing, 1 plus the square root of 3 would be somewhere over here. So in the first quadrant, so I know that this is my theta. All right, so now I know that Z is equal to 2 times the cosine of pi over 3 plus I times the sine of pi over 3. Okay, well now I can go ahead and use my De Moivre's theorem. So if I want Z to the 12th power, all right, I take 2 to the 12th power times cosine of 12 times pi over 3 plus I times the sine of 12 times pi over 3. All right, now 2 to the 12th is going to be very large, right? So 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, 2,048, so 4,096. Right, times the cosine. Right, 12 times pi over 3 is 12 pi over 3, right, which is the same as 4 pi, right, but 4 pi is not between 0 and 2 pi, not including 2 pi, so you'd actually have to subtract 2 pi twice, and you would get to 0. So now, do be mindful here that it was given to us in standard form. We just turned it into trigonometric form to make this math much easier. But since it was given to us in standard form, we want to answer in standard form. All right, so the cosine of 0 is 0. The sine of 0, I'm sorry, that was backwards. The cosine of 0 is 1, and the sine of 0 is 0. Of course, I times 0 is 0. Distribute this. So this is just 4,096. Right, so it was much easier to get to this than to actually try to multiply this thing by itself 12 times. Okay, so that's the benefit of putting it in trigonometric form and using de Moivre's theorem. Right, let's go ahead and try this again. All right, so we can again say, all right, well, r is equal to the square root of a squared plus b squared. So this is just going to be the square root of 2. Right, tangent of theta is going to equal b over a. That's just 1. Tangent is equal to 1 at pi over 4 and 5 pi over 4. If we were to graph this thing, 1, 1 would be here, which would be in the first quadrant, so my theta is pi over 4. All right, so z is going to equal the square root of 2 times cosine of pi over 4 plus I times the sine of pi over 4. So z to the 6th, all right, so the square root of 2 to the 6th, all right, is really just going to be 2 to the 3rd, which is 8. You could, of course, use a calculator for that, all right? And then cosine of pi over 4 times 6 is 6 pi over 4, which is 3 pi over 2. All right, again, it was given to us in standard form, so we should answer in standard form. All right, so this is going to be 8 times cosine of 3 pi over 2 is 0. And the sine of 3 pi over 2 is negative 1. So if we distribute, we're simply going to get negative 8i. Again, much easier than trying to multiply 1 plus I times itself 6 times. And we're not going to worry about nth roots. It gets a little messy, and I don't think it's overly required for this course, so we'll go ahead and skip that. I didn't put any on your Delta Math assignments either, so we are done for the day.